Okay, again, sorry for the delay. My microphone is should be a lot better now, but it decided to reboot my computer just at 10:40, and of course that can take a while. Yeah, thanks everybody. This is lecture 10. We are finishing audio part 2, and obviously we're gonna go through questions you may have. I saw a bunch on Piazza. I tried to actually respond to them. Hopefully that was good enough. Definitely you guys found a bug in TF meter. That's kind of cool. Then we will discuss the homework, and then again we do more on sound. This is going to be sort of the second lecture on sound, and then next lecture is going to be vision and multimedia. And from that point on, I will actually bring in one guest lecture that's going to be all about the measurement tools and how to use them. I'm thinking of getting Rishi in, and after that, I kind of want to hear from you about the projects, and then we will have more project discussions. And then at some point, the semester is going to be close to an end anyway. So, um, believe it or not, we're already like well into the Corona semester, basically almost being done. I'm not sure what happens next semester, but we'll see. Um, let's start with anybody have any questions? If there are no questions, let's go to the homework, right? Uh-huh. So what I'll do is I open the homework. So we had homework 5, um, and this was more of a thinking homework, and I'll put homework 6 up. Homework 6 is also the last homework. Homework 6 will be on today. So homework 5 is what is the memory equivalent capacity of a neuron with static weights, and the number of states this neuron can assume is independent of the input is 1, right? So it turns out um, if you have a switch that's set and you can't switch anymore, you don't have memory, right? And that means you have 0 bits of capacity, right? If you don't have memory, then you have 0 bits, right? Um, that's what it is. So the moment you have set your weights and you're static and you can't change them anymore, that's sort of what you memorize. You can read the memory, but it has basically no uh, capacity of storing any other function than the one it already has. And then in terms of information, that gives it 0 bits. But it is kind of interesting because it could be that you'd say, well, but if I read it, if I have to read those parameters, then they take some memory, right? And that's true. But in terms of the potential of what it could do, it has no memory because it's a constant, right? A constant does nothing. And then with A and mine, check the 4 rules on calculating memory equivalent capacity for neural networks to calculate the contribution of a convolutional layer to the overall capacity. And that's is the interesting part. Um, if you take max pooling, for example, it's just an argmax of the matrix that's coming in. So we're basically choosing, not closing, sorry, we're choosing one value of an entire matrix, right? Now the question is, how many bits can this value have, right? And then for an RGB image, each channel usually carries 8 bits. And so the maximum value could be 255 in each channel, but the actual maximum capacity is 8 bits. So whatever matrix you have, let's say it's an 8 times 8 times 8-bit matrix, then it would be 64 um, um, times 8. But if you now choose 1, then the maximum capacity, sort of the maximum that comes out of there, is 8-bit, right? So you have a quantization from 64 times 8-bit to 8-bit. And now these 8-bit that come out is what you have to say that's the amount of information that the next layer that's dependent on that layer actually needs to process. And that would be for one convolutional neuron, obviously. Um, and now if you could just say, instead of a single decision neuron, argmax is often used as a decision function. How does this change the MEC? And then it turns out, well, if argmax is a constant function, then it doesn't add capacity, right? It just, you calculate the capacity before argmax using the 4 rules. And then what you do is you just say, well, the maximum that come out is this number of bits. But also, really, argmax is just used as saying, well, I choose 1. Well, and so the capacity is nothing else but the probability distribution of how often each one is chosen, right? And if it's equidistributed, then it could be, let's say if it's three neurons, well, it says binary. Okay, if it's binary, then actually we don't have that. But even with two neurons where you do argmax, it would be maximally 50% chance for each to be chosen, and now you have again one bit, right? So what I'm saying here is you have to think about sort of what the output could be rather than looking at the function, right? The function is just a function, but what does it choose and how likely is it to choose something? That's how you get to information. Any questions about that? Because I think there could be, because that's convolutional layers, and it's a little out of what we have discussed. But the trick is, I'm hoping that in the homework you can get there. Okay, so if there are no questions, then we have the other one that was kind of nice. Assume you have a hard disk with 1 terabyte capacity. A friend wants you to give the data that she says takes 1.7 terabyte on her hard disk.
Professor,
Yeah.
I think someone in the chat mentioned they had a question.
Oh, thank you for alerting me. Awesome. I have a question. Yes, please just go ahead and do it.
Oh, yeah. So sounds like, just to confirm, sounds like the capacity of a convolution layer just depends on the output shape of it. So it does not depend on any other parameters, right?
Yes. So this is why you have this ABC, right? So if your convolutional layer has constants, if you're not training it, right? So um, if you're using, let's say, the convolution layers of AlexNet and they're pre-trained, then there's no more capacity for training, right? It's pretty simple. You can't switch anything, but they still act as an information reducer, and that's why you have to do these calculations. You have to ask yourself, how much information are they actually reducing, right? And that's what it
Right.
is. Now, if you're training the convolutional layer, then we would have to take a look at the number of functions that particular neuron or each particular neuron in the convolutional layer can actually assume. But that depends on how you train a convolutional layer, right? Does that make
So,
sense?
so the question B here is assuming that the network is pre-trained, right?
So question B is assuming that
The the
the
weights is static.
the weights are pre-trained. Yeah, B and C.
Okay.
So these are three different sort of things. A is um, just to alert you that once you trained, you had zero memory capacity because you have constants. The moment you have a constant, it disappears. It's kind of weird, right? Now, with that in mind, and it's actually even what it says, um, if you have a pre-trained convolutional layer, then you can still find out what the information reduction is by looking at those values. And then C is basically, wait a minute, but what if you use argmax not in that max pooling fashion, but as you have different output neurons, you use the argmax, which is very frequently done. Well,
Mhm.
again, then argmax isn't the point. The point is that what's the probability of argmax choosing one over the other over the other over the other, and you take the Shannon entropy of that. Um, yeah.
Okay, thank you.
Yeah. So now, again, if you were now saying, but I'm training something like a convolutional layer, then you have to see how many states can it assume, right? But that's different. Okay. So, expectations. Assume you have a hard disk with 1 terabyte memory, and a friend wants you to give data that says takes 1.7 terabyte. Would you trust your hard disk to store her data, given you have a compression algorithm at hand that typically compresses 2 to 1? If the data is typical, yes. But obviously, the point is in expectation, you're fine. But the problem is if she gave you random noise, then the answer is no. But if it's like lots of zeros, you compress even better, right? So in the end, the typical refers to sort of average data, knowing that some data will never be compressible and other data will be compressible by a lot. And the curve just looks like the Mackay curve, to be frank. It's just like, it's like, if you look at the Mackay curve, the sort of the curve that looks at the t and k function, and then with n divided by k at 1 and n divided by k at 2, you'll see, of course, that the curve asymptotally only goes against the x-axis. And what that means is that there's some data, there's some functions that, despite the fact that they're like super freaking, lots of rows in a table, they could still be compressed by a single perceptron, because again, asymptotically, there's like one or two functions maybe that can have, a million parameters and still fit into a single perceptron, right? And that's how this works, right? So if you have very sparse data, it has to be sparse, right? It has to probably be mostly 0 and then 1 or something, right? Very sparse data, you can always still, you can compress a lot. But in expectation, on average, it will be 2 to 1. And then we know there's no universal compression, universal lossless compression. And what that means is that some data will not be compressible, full stop, period, end of story. Okay. So in average, it's the expectation, right? So what could you do practically to estimate that the data would fit, right? And obviously you could start copying your 1.7 terabyte. And then the question is, what then? But the problem is that takes a while, right? So obviously you can do and just copy. But another way to do it is you start subsample. You start to subsample maybe 10% of the data, maybe 1% of the data, and see if that is compressible. And if you do so, and if that's compressible, then you start with a larger sample and so on and so forth, and then you can get an approximation of whether it can be compressed or not. And that's important because that is exactly the idea of sort of the capacity progression stuff that you see in sort of in the measurement tools that I gave you. And exactly that's what number C is: outline an algorithm, and then it becomes the generalization progression from the cheat sheet. And also, from groups and email, we already did that. Okay, so any questions about that homework? So also see we're getting way more practical about sort of stuff that actually matters. Okay, so then let's just go and finish the audio discussion. Okay, so more on sound. First of all, there was a good question last lecture that I wasn't able to answer. Shame on me. So remember we talked about decibel sound pressure level. And I said it's not a physical unit, only a scale, just like the bit. And it's basically totally convertible into bits, okay? So 8 bits is 48 dB, 11 bits is 66 dB, 16 bits is 96 dB, and so on. And then somebody asked, quite frankly, okay, but what's the conversion? And I didn't have an answer. So here's the conversion. You get the decibels by calculating 20 times log 10 of 2 to the power of n minus 1, where n is the number of bits. And of course, you can go the other way around. You just have to do the algebra to reformulate the equation, right? Now, the interesting part here is that people may ask, why is there 20 in there, right? So 20 times log 10. So first of all, there is a 10 in there because it's decibel. So a bell would be 2 times log 10. So the idea is that you have a tenth of a bell. Okay, that's why it's a decibel. But then also, why is the 20 in there? So why is it a 2? It's a 2 in there because they look at standard deviation, which is of course sigma squared. And that square, if you do the log of that, then you get the 2 in front of the log. Okay, that's where the 2 comes from. that makes it compatible to a Gaussian, which is obviously very useful in signal processing. Okay, so that's where the 2 comes from, just to remember. And other than that, 2 to the power of n minus 1 is obviously pretty standard formula. So the way this works is you actually get the signal level, right? So 2 to the power of a will be 256, minus 1 is 255 because you usually start at 0. And then you take the 20 log 10 of that. That's how you get to decimal. Any questions about this? Yeah, so this may not be so important for you, but it's actually just, if you ever hear decibel values, it's just good that there's just nothing else but ranges of signals that it could obviously be also expressed in bits or in standard deviations, right? Now, why does this become more important? Well, because these days nobody works with analog sound anymore, at least not in sort of in our profession. We have a microphone like I just have, directly goes into USB and it's digitized, right? So the microphone takes care of what you see here, which is basically binning the signal into digital bins so that you get integers out rather than sort of real numbers. And what you get of that is you see that you get quantization noise. And the way to not hear quantization noise, by the way, is to add a little bit of actual white noise to the curve, and then it works. But also, there are certain limits we need to obey. So obviously we can just do that. And then but the bigger question is, what is the stepping on the t-axis, on the time axis, such that I can reproduce, I can analogize from the digital, because that's how a speaker works, that I can go back to analog without losing too much. And that's that. So chapter 3 of Friedland and Jane. There's I explained it there, but in general, you can only remember this thing. 2 again, the 2 comes in again, basically with twice the sampling frequency. So if your time steps here on the t-axis are 200 hertz, right? So each line is sort of each second we sample 200 samples from that curve. Then you will be able to reproduce 100 hertz of frequency in analog. Okay, so you need 2 samples per frequency to completely losslessly reproduce the original signal. And so that is called the Nyquist-Shannon limit. And yes, Shannon had his hands in this thing again. They were actually quite prolific with figuring out how information works. So, so chapter 3 in my book explains this in more detail, but for really, I don't want to do a signal processing class here. So basically just remember, if you want to have, let's say, the full hearing spectrum, which is 22 kilohertz, you would use 44 kilohertz of a sampling rate. And that's important. So for example, when we had original analog telephony that became digital through the early cell phones, we used 8 kilohertz, 8-bit, and then there was some compression on it, because we know that we remember that loudness perception, volume perception isn't linear, so they companded it. They call it companding, which basically makes the louder signals represented with less resolution, and the more silent signals represented with more resolution. And it's called A-law or Mu-law. They're basically the same, except A-law is, I think, European, and Mu-law is the American version. But this was used for telephone for a long, long time. So you'll see a bunch of audio files that will probably have exactly that characteristics, where you have 8 kilohertz, 8-bit logarithmically companded. And then you have, nowadays, we don't do that anymore. We actually use full range speech, which is 16 kilohertz, 16-bit linear. That would be Skype, for example, and probably Google Hangout, and probably even Zoom. I'm not sure if they are higher at this point, but that's typically what's being used. And then if you have still a compact disc, which obviously nobody has anymore, but also that set the standard in the 90s for 44,100 hertz, 16-bit linear stereo. Okay, so that means you could have 22 kilohertz on it, which is pretty good, pretty, and the 16-bit and the 22 kilohertz pretty much capture most of the hearing range. And then we have 48 kilohertz, 32-bit linear stereo. That is when you actually record in the studio. You have a little bit higher, sometimes even 19.6 kilohertz. I don't know why they do it, but ultimately they want to make sure that when you edit the signal, that not too much is lost due to editing. And so um, 24 kilohertz is pretty much absolutely exhaustive, and 32-bit linear also is totally exhaustive of the hearing range. Um, so these are typical formats. And why would you have to know them? Well, you have to know them because if you try to train a machine learner on 48 kilohertz and then put in a 16 kilohertz signal, it's not going to work. Okay. So it's very important that your training and your testing, that these parameters match. Okay. It's really important. It will not work. There's all kinds of weirdnesses that happen if you try to mix those formats. Okay. Um, and this is just to show you the Müller companding. It basically compands 11-bit of an audio signal into 8-bit so that it fits into a single, 8-bit integer, which these days is not a thing anymore, but back then was a char, and that is kind of nice to have that. Or that a 16, two of them would be a stereo signal, right? Too, right? So that's what they did there. But I'm still introducing those because there's so many files that still obey this format. Pretty much anything that ends with .au, like you will see so many files that are still in this format that you should know, okay? Because if you train on them, you may just fail. Yeah, and then, by the way, we talked about microphones last time. And funnily enough, a microphone can be used as a loudspeaker, and a loudspeaker can be used as a microphone. Just practically, I would not recommend that because you'll break them. But basically, it works the same way. It's just when you play back, you put electricity in, and the membrane moves. And when you record, the membrane moves and then induces the electricity, right? There's weird effects in terms of electricity anyway, because if you have electricity moving the membrane and at the same time recording with the same membrane, yeah, there's weird dynamics. So we just ignore this usually, but yeah, it is kind of an interesting part of this. I don't want to go too deep into this because ultimately um, there's a lot of acoustics and physics and electrical engineering about audio, but I gave you a couple of sources on where you could read this and just get more ideas. Just like the microphones, it's important that loudspeakers have just the same characteristics like ball or cardioid or and so on, because they're ultimately the same thing. So that's important when you set up your home theater system, um, and also when you record something. But I think it's not that important for this class, but I just wanted to let you know. What's more important for us is let's talk about if you have some audio stuff and you have some problem with the audio stuff, what could you do? And a lot of this stuff is before neural networks, but I can tell you from my personal experience that it's also still useful. And in many, many times, just using one of those filters is extremely helpful. And then your neural network training goes so much smoother. Okay. So the first thing we should remember, I don't know how much signal processing you guys had, it's just a Fourier transform. Okay. Again, you could go to my textbook and go to chapter 8, which explains it in depth, at least on a sort of a practical application level. But it's good to know it. What it ultimately does is nothing else but take a amplitude signal and transforms it into a set of parameters of sine waves. Okay. And so it does this sort of frequency by frequency by frequency. And so you get a spectrum, right, which we discussed last time. So which is basically frequency on the x-axis and energy on the y-axis. Okay. And this is the formula for it. If you actually do it, you'll see it works. But in general, here's a pseudocode for it. If you want to try it out, it's also from a book. Reality is we were all saying deep learning doesn't need that anymore, except when I look at Microsoft Speech Recognizer, that's what they do before they put it in a deep learner. Okay. So it's still useful to know what a Fourier transformation is. Um, and then there's another one that you should know from signal processing if you ever took a class, which is called the convolution theorem, which is if you have two functions f times g is their convolution, then in Fourier space, you can do either the Fourier transformation of f times g, or you can splice it up into the Fourier transformation of f times the Fourier transformation of g, which is kind of nice because sometimes they can save a lot of time, but also that explains to us why, for example, a 2D and a 3D signal can be just individually Fourier transformed in each dimension, and then we just multiply them, right? So same here, and of course the reverse is also true. Okay, it's just something to keep in mind if you ever get into trouble. Like, how do I do this? Yeah, you do this dimension by dimension, or whatever your convolution is. Okay. Um, Another very important tool in the audio realm is this. It's called a bandpass filter. So a bandpass filter is basically you can select the frequencies and then you can select amplification or reduction in each of the sort of frequencies. Okay. Basically, for example, if you take the lower frequencies, you would get rid of the bus, and if you get the higher frequencies, you would get rid of the treble. Now, take a look at this particular one. This equalizer here is, by the way, implemented by me, but doesn't matter. A long time ago, this equalizer actually obeys the standards. It obeys. There is an equalizer standard, and that's actually sort of a professional equalizer. And the most important thing you can see is that the frequencies down are basically doubling, right? It's 31, 63, 125, 255K on one, and so on. And that's usually how it works. And then you have a dB range that's quite huge. If you put like something in the middle completely up and something next one completely down, your signal will be distorted. It'll sound like weird. Okay. So I know that, sort of in the 80s and 90s, you probably saw these little stereos that everybody had, and had like 3 of them for an equalizer. Reality is, this is a real equalizer, and with a real equalizer, you can really damage the audio signal, and that's what it should be, because then you can also really correct something if something is wrong. Now, this particular setting, by the way, that I show here is very good for speech enhancement. Okay, so if you want to listen to something better that's speech, take that setting. And in fact, it's if you go on Mac OS and take the equalizer out and say speech setting, that's the setting you'll get. It's also standardized in all kinds of ways. Yeah, just for your information. The other thing that we often do is called a dynamic range compression, right? So it's something where you go and say, well, let's take the input and make, let's say, stuff that's not so high volume, higher volume, and stuff that's high volume, lower volume. Okay, where basically when the range is this, you just make the range smaller. And or you could have dynamic range expansion too, where you basically say, hey, let's make everything larger, or let's just make the high tones larger and the low tones and so on. Again, something you should know before you do machine learning, because if you have data like this, it's going to screw you up. If you train on dynamic range compressed data and put in regular audio in that doesn't go through the same dynamic range compression, good luck having your neural network figure that thing out. Okay. So that makes audio always a little bit more tricky, because there's so many pre-processing steps that could happen. That's also why I'm explaining them. Then you have here's an example of dynamic range compression that is, for example, very useful for microphones. So if you have a microphone, if you're close, then you see it's a lot more amplitude, a lot more volume. And if you're far away, then you maybe hear nothing. And so the trick here is you could automatically help that with a dynamic range compression, where you basically go and say, well, if I'm further away, I'm amplifying, and if I'm closer, I'm decreasing the signal. But also, dynamic range compression is highly nonlinear, and as I said earlier, be careful, because your ear doesn't hear it. Your ear actually likes it; it's very pleasant, but your neural network will not like it. um, then we have something that's super cool called filter by example. That almost sounds like machine learning and pretty much is. It's kind of early machine learning. Um, what we did there is, for example, if you remember, you could have a hum sound like from the electricity, 50 hertz, 60 hertz hum. And the typical thing people would do to get rid of that hum sound when it, for example, accidentally gets into the audio because a long cable served it as an antenna or something, right? This kind of thing happened. They would use a thing called spectral subtraction. The way to do it is to basically record your hum, and then you really literally all you do is you get into the spectrum of the original signal and the spectrum of the hum, right? And you literally in frequency space just subtract the hum from the rest, sort of and then you go back to amplitude space, and this is what you see here. Okay, so this is like 3 seconds of a signal, and what you see here is some speech that was very much distorted by a 50 hertz hum, and then once you do the extraction, you see the second curve, which is the light, more light blue in front. That's actually much clearer speech than what was there before. And it almost feels like magic because wow, in amplitude space, it doesn't feel trivial at all how to subtract the two signals to get to the nice clean signal. But in frequency space, you can. Right? This is part of the reason why we have frequency space. We can just subtract the energy, and then this component is out. Okay. And now people were saying, yeah, but couldn't we do something more intelligent? And again, I think we're getting close to machine learning age where they were saying, okay, and I remember you asking a bunch of questions here in this lecture too about this. Is this something we can do to get rid of noise? Okay. And there's something, it's called a Wiener filter. A Wiener filter is probably the standard tool that was used before any intelligent signal processing to get rid of noise. And again, be careful when you have stuff processed like this. It can sound just better, but it has a weird nonlinearity on it that may need an extra layer in a neural network to dissolve, right? So what we do here is we say, look, in reality, we have a signal S of t that consists of a signal, but really we cannot observe the signal. We can only observe S of t plus N of t. And if that reminds you of my cat example in the thermodynamic channel in machine learning, congratulations, that's exactly the same thing. So S of t plus N of t is what you observe. And the question is, uh, and and then the question is, can you find a convolution that you get to S of t back, but we're honest to each other and say it's going to just be S head of t, right? It's basically something close to that. And again, if that reminds you of what I've presented before, for example, with getting the noise out of the images and figuring out the trade-off between generalization and memorization, again, same trick here. So now we assume the signal is that, where again, S of t is the original, N is the noise for, and S head, which I forgot the head, is the estimated signal. And then G of t would be a filter that we adaptively train on a bunch of signal to get there. Okay, again, sort of early machine learning, but it's so frequently used. It would be a miracle if you work with audio, except if you work with audio and just do one project in my class, maybe you won't find any, but there's so much stuff that has been processed this way, especially speech data, that is absolutely important to know that this thing exists. Okay, so GFT is the Wiener filter. So now how do we get to GFT? Well, we basically need a training signal, right? So we basically take a bunch of empty noise and we'll say, well, this is our noise. And we'll then say, well, we have this alpha, so we have S of t plus alpha minus S dash of t. And then you just do some math. You just define an error, right? You just say that's our error signal. And then also there's some delay in the signal. So it does both. It gets rid of the noise, but it also tries to help with the delay. And then you get, here we go. You can get to the Wiener filter in this way. So I don't want to go into too much detail, but ultimately what you need exactly is you have the power spectrum of the signal and you have a noise footprint. It's the power spectrum of the noise. And then you can get by sort of, estimating the multiplication you have to do with a polynomial into what's called the frequency space Wiener filter. Okay. Um, Again, I think this is something you look up if you run into it. I just wanted to show you easy techniques before machine learning and how do we do this. And again, the problem here is how do you know the noise? And the only way to know the noise is to get a footprint. The problem is how do you get a footprint of the noise? Some systems would basically just record empty signals. They would basically say, okay, for example, if there's very low amplitude, we consider that noise, right? The energy is very low at this point, we consider it noise. Yes, so the better way and the more typical way we handle audio now, especially in the cell phone age, is to use microphone arrays, okay? And they're very, very popular, again, with cell phone people, with sort of meeting recording people, with a bunch of people who want to capture audio from a far field situation, right? And the reason why we have multi-channel in the phone is that you can actually start your phone in the car, right? So stereo popular since the 1960s. We know this, but and by the way, also most cameras have stereo microphones. So ultimately, whenever you encounter audio, nowadays it's actually microphone array, but also since the 60s, it has been stereo. And most cameras, even like if you record audio with a camera, you do some video recording, they will record stereo at least. And then I'm actually surprised. There may be some Android phones who now do actually multi-channel, or 8 channels or something. And now, of course, now then there's an interesting question. In the image space, right? When you have R, G, and B channels, you either put them together or you treat them separately. But how do you do this with audio? Um, Especially um, um, because audio has the speed of sound, and I will show in a bit. But there's also special stuff like most DVDs are encoded 5.1. Now, if it's digital tracks, you're fine because then all the information is in there in the digital. If it's not digital, then you have Dolby Surround and the stereo track, and decoding that is actually quite hard. I will show it in the next slide. But the interesting part here is for all of these, you have to be very careful how to actually put them together. Okay. They're not meant to just be put together. You can do it with stereo pretty much, but even that is a problem. Really, you have to treat them separately, but then it's also not clear how they contribute. So I'll talk about how to put these together in the next couple of slides. So first of all, if you're Dolby Digital, you should know that, like, in a living room, often people have now these 5.1 systems. These are Dolby Digital, Netflix, and Hulu and HBO. They all send their signal out in Dolby Digital at this point. And the idea is you have a home theater, and basically you have left speaker and right speaker in front, left speaker and right speaker in the back. That gives you sort of a circular ambient sound. Sort of, if something happens in front left, it's there. And in the back right, it's there. That makes sense. But then you have two other speakers. The number 5 is the center speaker. That's the speech speaker, because people figured out they actually kind of want to hear people talking in the TV. It's just what it is. And then you have the point 1. The point 1 is usually just a bass speaker that gives you sort of oomph. And it's called point 1 because it only takes a small frequency range, and you cannot locate it. So you can put that speaker wherever you want, because our audio in the ears cannot locate where the oomph comes from. It's just in the room, and that's very nice because now we can put that big bulky thing wherever we want. I would just say don't put anything too close to it and don't put anything on it, because it will distort the sound. Other than that, put it anywhere you want. Um, Again, I don't want to educate you too much on how you do your home setups. That's why I gave you a source for that. I want to educate you, however, what happens if you, let's say you want to do some audio recognition or some machine learning task on a Dolby or Dolby Surround DVD. And in fact, I've done this. I can show you some projects I've done. it actually is not so simple, right? I mean, you could hope that YouTube takes care of this now, and maybe the conversion to digital does it, and you can use that signal. But if you had to do it by yourself, where you actually have the DVD, that's what you have to do. So what happens there is they put the Dolby surround into the stereo signal. So in reality, they only send two signals. Um, they only send left and right. And if you put it on regular speakers, everything is fine, right? It's just going to be stereo. But if you have a Dolby surround decoder, you actually get the left, center, right, and surround. Okay, you actually get four channels, and that's kind of interesting. Most people don't know that. There's a really, really smart encoding scheme that Dolby patented, and having a Dolby surround decoder, by the way, costs money still because you have to pay license fees to the patent. It's a really smart thing, but here's the problem. For you, it appears as a stereo signal, but it's not. It's actually phase shifted. So if you have some other stereo signal that's an actual stereo signal and the Dolby surround signal, and you try to match them using machine learning, you're going to be in trouble. Okay. This lecture sounds like a lecture where I'm telling everybody, audio is complicated, don't use it. It's not that bad. I just want you to avoid pitfalls. Okay. So how do we cope with multiple channels if we have them in general, right? It's called, is either, there's a couple of ways, but first way is obviously treat them differently, right? Different channel equals different content. Let's see what happens, right? Um, Better, however, I think, is to combine them, and because that can lead to just reducing noise. And what you need to do is you need to cross infer between the channels, um, either sort of using machine learning or using what I tell you next, which is called beamforming. Um, and the way to do that is to actually delay and sum the signal. Okay, so what is delay and summing? So when we have RGB, the speed of light is so fast that the light ray who has to get into the R, the G, and the B sensor will actually appear to, even though the sensors are physically apart, even though very little bit, only obviously will assume it's the same time because light is extremely fast. Okay. But um, sound is not. Sound is just the speed of sound, and that's a lot less. And so what happens if you have a microphone on one end of the room and a microphone on the other end of the room, there's actually going to be a delay. So while the same signal is recorded, even if the same identical signal would be recorded from the same source, there would be a delay because if one microphone is closer and the other microphone is further, then the sound arrives at the further microphone at a later time. And so what we have to do here is not just average the two signals, we have to actually match their peaks. Okay, and that's called delay summing. And there's also what's called a frequency domain beamformer, right? But in both ways, you have to sort of normalize the speed of light out. And yeah, so there is, if you need a beamformer, there's a really nice open source beamformer that I know has been done by my friend basically 15 years ago, but it's still the standard. It's from Javier Angera. His PhD thesis was a really good beamformer that so many people use now. So and yeah, you could just use this, and he did a delay sum beamformer that basically tried to find the peaks and then average them, and you go from 8 signals to one really clean signal. It's really nice. Again, don't want to go too deep into it because it's a specialized problem, but you may run into it, so you should know about it. Again, the output is the sum of all channels with lower noise. And also, by the way, you get the delay between the microphones. So it's not just the audio signals clean, but also it'll tell you the delays that it measured between the microphones, which helps you locate sort of objects in the microphone. That can also help you sort of with, let's say you have a video localization task. You could use that audio, that delay to figure out where in the picture something is. Okay. So that is all about the pre-processing for even just regular hearing and reproduction of audio. I'm now going to show you pre-processing for basically machine learning and what has been done and what you could see and what you could find sort of traditional old pre-neural network machine learning. But again, these features are still useful, and also you find them all the time. You want to know what this is. So first of all, when somebody uses energy features, it's usually just calculating the root mean square of a window of samples. Okay, you say, okay, the 10 millisecond energy or the 1 second energy. All you do is you take all samples, root mean square them, and you will be surprised. This is the most basic prevalent feature. It'll help you with so many things. It'll just work. Okay. The typical use obviously is squelching. Squelching means if you hear some sound, then you transmit it. And if it's just noise, if the energy is too low, you just put it to zero, right? Um, and that's very useful. So you don't hear anything except when something is being said, right? Um, and yeah, it's usually meant for is there audio at all, right? Then another one, which might be very interesting, mostly for specialized tasks like is it voiced or unvoiced? Do people know what voiced unvoiced means? So voiced is my sound is voiced right now, but unvoiced is if I talk like that. It's like if you whisper, for example, then it's unvoiced. But also you could use that in music to see if it's singing or talking, right? And the prevalent feature there is kind of interesting. It's called the zero crossing rate, and that's nothing else but figuring out how often does the sort of sine wave of the sound actually go through zero, right? Because if it's unvoiced, it doesn't go very often, and if it's voiced, it does. Um, and it's also really really useful because all of us when we talk have a specific zero crossing rate, and so if that changes then something changed, right? So that is an early anomaly detector, and for example we used it for overlapping speech detection, basically saying, well, look, we have these two people in a room and they have specific zero crossing rates, but the moment they talk above each other then obviously all kinds of stuff happen and the zero crossing rate goes through the roof, and we can detect that. Okay, it's not a sufficient criterion for detecting that or detecting anything for that matter, but it's a very good feature if you ever need one. The other one is pitch. Okay, and pitch is usually done using autocorrelation, where all you do is you say, okay, do I see that signal again? um, it unfortunately is computation expensive. If you see that what it does here, it really just tries all kinds of correlations of the signals, um, and it will fail. By the way, it's not an easy method. This is the most basic. It's also described in my book, but the pitch estimation itself honestly is ongoing research to really find out what the pitch of a signal is, if it has a pitch, because there's also unpitched. um, then yeah, that would be great. And that's something, by the way, where I wonder if some neural network with recursion could do a much better job than sort of this standard method. And I think it could, because it could train itself to be specific to the kind of signals that we put in, rather than being sort of a generic method here. So I agree. I think that's a pitch detection, something that could be worked on with sort of a typical LSTM or something approach. And then there's something that almost sounds unbelievable. It's called harmonic to noise ratio. So for example, when you can extract the harmonics, but you need a pitch detector for that. So let's say you have some decent pitch detector, then you can actually go and say, okay, um, what is the harmonic? What is the pitchy content versus the not so pitched content? And that gives you a lot of stuff. So you can distinguish speech from music, types of music, but also there was a PhD thesis in 2006 that you can actually look at speaker age. Okay, you can actually find out the age between people using that. It makes total sense, because as a kid you have a very voiced, very harmonic noise, and then if you become a grandma, then it's going to be more and more not so nice. And then we have LTAS, the long-term average spectrum, which is often used as an indicator for type of audio. For example, speech versus music versus types of music. Um, and that is a very interesting one too, because really what all it does is, instead of using an FFT on like a 10 millisecond or 100 millisecond window, you will use an FFT, let's say, on the entire file, right? or maybe 10 seconds or something. It's called long-term average spectrum, and as you do so, you'll obviously get the average spectrum out. And if you look at the signal, you right there see that's pretty much speech. Um, and if it was more on the higher frequencies, it could be a symphony concert, right? So that helps you distinguish types of audio. Again, speech versus music or types of music. It's a very good feature, actually. I'm pretty sure you could train some good discriminators based on this. And before we go, so these are just basic features, right? Before we go into more interesting features, I'm going to just show you how these features look like. Okay, so a typical speech signal is up front, and then you have pitch. Because not all regions are pitched, you'll see that there is the pitch track. It's called a pitch track. The pitch track has sort of holes in it, okay, for the unpitched parts, like doesn't have a pitch, right? So from pitch actually is a good word. Only the has pitch, right? Everything else doesn't have pitch. And then energy obviously just looks the same as the original signal, except it's the positive. And then you could have so-called formants, which is just basically different ranges of spectra where we sort of look at it's supposed to correlate with different parts of your vocal tract. And then you have harmonics to noise ratio, which is down on the bottom. These are just some basic audio features. You'll find them in a bunch of tools, and I will show you those tools in a bit anyway. Now, better and more used features for machine learning, or features that have been used for machine learning for 30 years, are those, okay? The most important one I'm going to explain in a bit. It's called Mel Frequency Scaled Coefficients, MFCC. You may have heard of them. They're still used. Siri uses MFCCs, okay? Who else? Okay, Google uses MFCCs, okay? Even though they're all doing deep learning, they're still using MFCCs, okay? And there's a reason for it. I'm going to explain how they work. There are other features, basically in the olden days when we were competing about features, people were coming up with all kinds of stuff, of which the most important one would be linear prediction coefficients. Linear prediction coefficients came from speech synthesis. If you ever remember, if you go to a museum, the Speak and Spell used LPC to synthesize voice. Obviously, you can go the other way around and desynthesize. Then there are other features, but really the one feature that won in the end was Mel frequency scaled coefficients, MFCCs. And unfortunately, it's the feature that has the least mathematical backing. Let's take a look at it. So this is how MFCCs work. You do some pre-emphasis, which is just, scaling it by something. Then you window your audio, which is basically saying, let's take 30 millisecond windows, okay? So you take your audio and split it down into 30 millisecond chunks. Of that 30 millisecond chunks, often there could be even sub-blocks where you do 10, 10, 10, right? But it doesn't matter. So first of all, let's take our 30 milliseconds. And then we use an FFT, which is just a Fourier transform that I was showing you. So we put it into the spectrum, okay? So now we have spectral features. And then we scale them by what's called a Mel scale filter bank. We already know that when you have a spectrum, the acoustics, the ear will not hear each frequency with the same volume, even though it may have the same volume. So we can normalize those and we can just say, okay, if we wouldn't hear a certain frequency anyway, let's just get rid of it. And that's the so-called Mel scale filter bank. Then we logarithmic scale it because also, again, volume perception isn't linear, it's logarithmic. Remember Euler, right? And that's the weirdest thing of those, right? All of these steps seem normal. But then we do a DCT, so another Fourier, or a DCT is a discrete cosine transform. We do another spectral transform on the spectral transform. Okay, so we got to the spectrum already, did some transformations, and now we go again to another spectrum. And because that's so weird, they decided to call that capstrom instead of spectrum. Okay, it's the capstrom. So that's what it was. That's what it is. So now it's kind of weird. It's called Mel frequency capstral coefficients because we have the Mel bank in there and it's frequency anyway, but also it's capstral, not spectral. So they figured it's so weird, we call this capstrom. Now, what does this do reality? Well, first of all, let's take a look. Um, if this is your audio signal, right, the original signal in the Fourier space, okay, then you go and do that Mel scale, which is, here's a Mel scale filter bank on the bottom. It just looks like this triangular shaped thing, which gets rid of some frequencies. And so the input audio on the left goes to the FFT, then you go to Mel spectrum, and then you go to Mel capstrom. And what do we see? Well, 10 milliseconds or 30 milliseconds of audio, right, depending on your frequency, uh, is a bunch of values, right? It could be like 10 milliseconds could be like 160 values, right, with 16 kilohertz. Um, so those 160 values end up being 19 values. So it's a huge compression of that space, but it's sort of perceptually motivated. And doing the spectrum of the spectrum to go from the capstrom is actually sort of an approximation of PCA. It's basically, the idea is to just get rid of correlations and have the signal as uncorrelated as possible, to just have sort of what's really important in the signal. Um, Now, how well does this work? No idea. Do we have a proof that this is great? No. But is every speech recognizer on Earth has been using this for the last 40 years? Yes, absolutely. So we have to live with this hack when we work with speech recognition data. And if you ever do that, you'll definitely come across these features. And they're called usually MFCC and then a number. And the number is the dimensionality reduction. So the second DCT, the second spectral conversion to capstrom, is obviously determining how many coefficients come out. And so for speech recognition, often we use 12 only, right? So then the 16 kilohertz, 160 goes to 12. So it's a factor 10, even more. And then for speaker diarization or speaker identification, sort of figuring out who the speaker is rather than what was spoken, often it's MFC 19, so a little more, because the higher capstra seem to give us the speaker. And then delta and delta delta is when you go and say, well, okay, I'm taking MFCC 12, but now I'm also taking the deltas between those coefficients, would be 11. And then the deltas between those deltas, the delta deltas, would be 10, right? So you end up with 12 plus 10 plus 12 plus 11 plus 10 when you have MFCC 12 delta delta delta. Okay. And why do we do this? Because it works. Okay. I cannot give you a better reason than it works. And it still is in Siri and in Google speech. It's been something people have been working with for so long that it's not even clear anymore. I mean, as far as I'm concerned, we should completely replace those features. And so now, because I said that, I want to also put my mouth where, my money where my mouth is. And here's what I did. I created a speaker ID system where we used LFCC, sort of no Mel scale, just linearly frequent capstra. So all we did was the same transform, except we left that Mel scaling, frequency scaling out. And then we did and said, okay, what if we do anti-Mel scale? So we basically make everything bigger that is not perceived and everything smaller that is perceived. We just reverse the Mel scale. And guess what? Machine learning didn't change. So in the day and ages of machine learning, it looks to me like we don't need those MFCC features anymore, except they're still used. We're still using them. But also what I didn't try is doing capstral. And basically not doing capstral, right? So I just tried to see what the Mel scale does. And in the day and age of machine learning, the Mel scale doesn't do anything anymore. So in the last couple of minutes, I will not bore you with further sort of best practices. I'm going to give you just tools you can use. So if you ever want to edit audio, and the tool that was also used in the tool in the video last time, Audacity is your friend. Audacity is a really good tool. I know the main developer of it, and I think he works for Google now, but that's usually what happens. Point is, open source is a really good tool. Then we have something that's super historic, but I'm still introducing it because it's being used by so many people still. It's called Wave Surfer. I would actually not recommend this tool, but you may come across a file format that needs Wavesurfer to load, because Wavesurfer gives you either the waveform or the spectrogram, as you can see here, and then you can annotate. As you can see about below the time, you see the lab, sil, k, and so all of this is basically a speech annotation program. Okay. And while I don't think you'll do any speech annotation in this class, you may come across speech annotated files that need to be loaded using that thing and then exported into something else. So that's why I'm giving you this tool, Wavesurfer. Another tool very similar to Wavesurfer, more like for analysis, and if you ever want to try out these features, is Prot. We actually created something called Prot Lib that you can download so you can programmatically get those features out. That was really nice. It's called open source. Open source Prot means speech in the Netherlands. And so we worked with the developers of Prot to just basically do that. And yeah, there was a bunch of interesting stuff we could do with those features. Most likely not what you need to do, but if you want to try look, see what features do for versus not using features, Prot, is your friend. Um, Other useful tools just for sort of command line use is socks. Socks will convert and filter and play. Okay, socks everybody needs socks on their computer. Okay, that's what it is. And then there's FFmpeg, which actually is more useful for next lecture because it's doing both audio and video playback and conversion, and it's open source, so you can hack into it. And I know some people in my multimedia group, they got a patch from me. I think Arjun is working with it, and Alex maybe too, on sort of an FFmpeg patch that, for example, extracts motion vectors and these kind of things. FFmpeg is really the way to go for this. If you just want a player, and also something that can actually play DVDs with Dolby Surround and all of these kind of tricks, you should use MPlayer. But that's not an easy program to hack. So FFmpeg is better if you want to do something programmatically. And then there should be two more slides. Another slide is HDK, previously owned by Microsoft, I think now owned by Google, is a speech recognition, a full speech recognition suite that is kind of easy to use. And also you can just try it out with a GUI. So if you ever need a speech recognizer for some intermediate, you can use HDK. You can also use Kaldi. Kaldi seems to be the more interesting one these days. There's also Pocket Sphinx and Sphinx. All of these work well. HDK seemed to be the standard for a long time. That's why I'm showing it. And then two more things. So there's a Python library for audio analysis that was being created by my friend Dan Ellis, who used to teach at Columbia and now also works for Google. And that's called librosa. Librosa will, generate your MFCCs. It will generate all of these features that we were discussed with an outlook on machine learning. Okay. And then there's one more thing, which is the Princeton Sound Lab. The Princeton Sound Lab has all kinds of software, but most importantly, it has visualizations of sounds and sound transformations and sort of feature extraction like LPC. And so I really want to show you this because you're going to get a lot more visual about how audio actually works. It's really, really nice. Yeah, and I think that's all I have for today. I know this was a pretty intense lecture with lots of stuff, but it's mostly a lecture where it's a lot of reference. And I see there's a question. Okay, Arjun says FFmpeg is great for video conversion, deconstruction of videos into component frames, as well as motion vector visualization. Thank you, Arjun, for backing me up. Yeah, so as you start working with audio, take a look at those slides. And if you don't work with audio, obviously it's not important, but it's good to have those in case you ever work with audio. And to be frank, we should be thinking more and more multimodal. So that's what's going to happen. Okay, so I'm going to now stop sharing. And then also stop recording, I think. But where's my recording right now? Weird. Maybe I share again and then I find it again. Okay, yeah, because now I can actually say stop recording. Okay, well, first of all, thank you everybody.